Let's try to solve this problem here. So we are given with a diagram which shows a very weird looking slope with point position A, B, C, D, with a ball now at position A having an initial velocity of u. This position A is 10 meter above the ground. Okay, so a ball of mass 0.5 kg, let's write down 0.5 kg, is at the point A. Okay, you can see in the diagram is at point A with initial speed of 4 meter per second. So let's write down 4 meter per second at the height of 10 meter as shown in the figure above. So it shows here it's 10 meter. Okay, next they ask you to determine the total energy at point A. So total energy here, I believe they are asking for the mechanical energy, because total energy it's a bit vague. What is total energy? It can be including something like internal energy or sound, or yeah, there's many types of energy. But I believe that since you're in chapter 5, when they say total energy, it should be referring to the mechanical energy. So if that's the case, well, it's just the sum of the kinetic energy and the potential energy. So let's try to write it. So the total energy, or we write it as mechanical energy at point A, will be equal to the kinetic energy at point A and the potential energy at point A. To be more specific, is the gravitational potential energy at point A. There will be no elastic potential energy since there's no elastic material here. You see no spring in the situation. So we know that the kinetic energy is half mv squared. This is the speed at point A plus mgh, where now this is the height at point A. You can perform your substitution now by substituting in the mass, substituting in the speed, which is 4 meter per second at point A. Then you can substitute in the mass again, 0.50. G is just 9.81. And the height will be 10. Okay, so once you have substituted in everything, you should get an answer of 53.05 joule. Okay, now here's the thing. This question, right, technically any answer is possible. Why do I say any answer is possible, right? Because here you have something called the potential energy. If you remember from my video that I explained about potential energy and kinetic energy, potential energy, right, it depends on where we set as our reference position. Here, right, we are setting the ground as the reference position. Actually, we are sitting here as our reference position. Reference position is where we set our h to be 0, thus causing our u to be 0. Okay, but this reference position can be anywhere. I can actually set the height of C. Let's say I can set the height of C as our reference position. Then our gravitational potential energy will be the difference of height between point C and point A. And it will be a negative gravitational potential energy at point A if we set point C as our reference position, because point A is at the height below point C. So if we set our reference position to be point C, then it will be a different value. If we set our reference position at point B, then our gravitational potential energy will be a different value. But for now, we are going to be setting the ground as our reference position. And if we set the reference position to be the ground, then our mechanical energy will be 53.05 joule at point A. Okay, so again, the gravitational potential energy can be any value because it depends on where we set as our reference position. Potential energy, we don't usually care the exact value of the potential energy. What we care the most is the change in gravitational potential energy, because that will represent the work done by gravity negative. Okay, negative work done by gravity. As you have explained last time, the change of potential energy right here, change of gravitational potential energy is just equals to the negative of work done by gravity. Okay, so the thing that never change is the change of gravitational potential energy. But what is the gravitational potential energy at a certain point can change, depends on where we set as our reference position. Okay, next, question 2. The speed of the ball at point B where the height is 3 meter. So at point B will be having a height of 3 meter above the ground. They are asking for the speed of the ball at point B. Well, we'll be using our conservation of mechanical energy over here, but I won't be explaining why this situation here the mechanical energy is conserved. If you wish to know why in this situation the mechanical energy is conserved, you can refer to the previous video, example 1. Okay, because example 1 we look at what are the conservative forces and non-conservative forces acting on the ball. From there we'll try to determine whether the work done by non-conservative forces is equal to 0 or not. And from there we check that if the work done by non-conservative force is equal to 0, then our system here will obey the conservation of mechanical energy. In this case, it will obey. You can check it by yourself by drawing the free body diagram. But I'll just write it like this. So I will compare between two different positions. One position where I know most of the information, if not all of the information. One position which we are interested to find something out. The position where we are interested to find something out will be position B, because at position B we are interested with the speed. So definitely we need to have position B in our equation. What else? Another position will be the position which we know most of the stuff. So this will be position A. Okay, so we'll be comparing between position A and position B. So you have mechanical energy at position A is equal to the mechanical energy at position B, because the mechanical energy is conserved throughout the whole journey. So at any point, the mechanical energy should be conserved, should be the same. Okay, so this will be kinetic energy at point A plus gravitational potential energy at point A equals to kinetic energy at point B plus gravitational potential energy at point B. Break it down. This will be half mVA squared. This will be mgh at point A. This will be half mvb squared. This will be mg height at point B. Okay, now I believe it's a matter of substitution. Let's do it. So this is half 0.5. The speed is 4 at point A plus mass acceleration due to gravity. The height is 10 meters above the ground. We set the ground as our reference position. Next, half 0.5. We are interested with the speed, so leave it at VB squared plus 0.5, 9.81, and the height at point B will be 3 meters. Okay, so all the values are already substituted in except for the speed at point B. And since this is the only unknown in this whole equation, I believe if you use your calculator to shift things around, you will get your VB. And in this case, VB, speed at point B will be equals to 12.4 meter per second. Okay, very straightforward. Just take two positions and compare, substitute in everything, then your answer will come out. Okay, next question. The speed of the ball at point D, which is the speed of the ball after it finished the whole journey over here, reaching point D. Again, we'll take one position where we know most of the stuff, then we'll take another position which we are interested to know something about. We are interested to know about the speed over here, so definitely your equation should have position D inside, and pick another position which you know most of the stuff. You can pick position A, because you can determine the kinetic energy, you can determine the potential energy. You can also pick point B, because point B you know the height, you can determine the potential energy. You know the speed from question 2, you can calculate the kinetic energy as well. So point A and point B can be used, but again I'll be using point A and I'll compare it with point D. Okay, so question 3. be taking position A and I'll compare it with position D. So again, it will be kinetic energy at point A plus potential gravitational potential energy at point A equals to kinetic energy at point D plus gravitational potential energy at point D. Then it becomes half mVA squared plus mg height at point A equals to half mvd squared plus mgh at point D. Next is just substitution once again. Half 0.504 for the speed at point A, 0.50, 9.81 for acceleration due to gravity. Then your height is 10 meters above the ground. You set the ground as the reference position. Next, half m, you need the speed, so leave it as vd squared. Next, it should be 0.5, 9.81. The height at D will just be 0 because the D is right on the ground. So if you are on the ground, then the height should be equal to 0. So because we set the 0 as our reference position. Okay, so now with everything being substituted in, we are left with the speed of D as the only unknown in the equation. So now if you manipulate things using your calculator, you should be able to get your speed at point D, which will be equals to 14.6 meter per second. Okay, until now everything is still quite straightforward. Let's move on to question 4. Question 4 asks for the maximum height of point C so that the ball can pass. Well, this is a similar question to the previous example one where we talk about the maximum height for the ball to stop at point C. Okay, the idea is that if this point C over here is a very low, it has a very low height, let's say the peak is lower here, then the ball can easily go past point C and go towards point D because only a portion of the kinetic energy that you have from position B is transformed into potential energy. So you still have some kinetic energy left, thus the ball will roll over point C with a certain speed. Okay, the speed will not go to 0, so it will not stop throughout its journey passing through C going towards D. But as you increase the height of point C, what will happen is more and more bigger portion of the kinetic energy at position B will be transformed into potential energy. So you are left with less and less kinetic energy when you reach point C. We are left with less and less kinetic energy. Thus, if the peak gets higher, if this position C gets higher, you reach position C with a smaller or lower speed. Okay, you get slower when you reach point C if the height of point C gets higher. But at a certain height of point C, what will happen is the ball will transform all of its kinetic energy into potential energy to be stored once the ball reaches point C. Then you are left with no kinetic energy. All of the kinetic energy has been transformed into potential energy, left with no kinetic energy. Thus, the ball will reach a stop. Okay, it will reach 0 meter per second once it reaches the peak at point C. Then slightly it will tip over to the to go over the slope, then roll towards point D over here. So the maximum height is the height where the ball will reach 0 meter per second at the tip. With a little bit of inertia, then it will roll over and continue to go towards point D. That's the idea of the maximum height. So we should expect the speed at point C to be 0 if you want to determine the maximum height. Let's try to do that. So again, our point that we are interested to find something, it's point C. So we'll be comparing point C with another position. Let's also compare it with point A. Again, you can choose to compare with point B, you can choose to compare it with point D. Just that for now, I'm comparing point C with point A. Okay, so this will be kinetic energy at point A plus gravitational potential energy at point A equals to kinetic energy at point C plus gravitational potential energy at point C. The starting is always the same, okay? So now we bring in the formula for each of the energy we have here. This is half mva squared. Then you have mg height at point A. Then you have half mvc squared plus mg height at point C. Okay, so now let's do our substitution. Half 0.50 for the mass, speed at point A to be 4, plus 0.5 for the mass of the ball, 9.81 for acceleration due to gravity, height is 10 at point A, then you have speed at point C to be 0, because I want the ball to be just at rest once you reach the peak. With a bit of inertia, tip it over and continue to roll towards point D. Okay, plus you have mgh, but you are interested to find the h, so h is something unknown for this case. So the height of C is the only unknown in the equation here, so you can use your calculator to determine height at point C. So height of point C will be equals to 10.8 meter, and this height here will be the maximum height. If your height of point C is above 10.8 meter, what will happen is the ball will not be able to reach the peak. Before it reaches the peak, the ball will exhaust all its kinetic energy being transformed into potential energy, so it will stop somewhere not reaching point C, then it will roll back down towards point B. That's what happens if your height of point C is above 10.8 meter. But if your height of point C is below 10.8 meter, what happens is the ball can roll towards point C while still having some remaining kinetic energy. So it won't reach 0 over here, it will still continue to roll over point C with a certain speed. That's what happens if your height at point C is below 10.8 meter. Okay, so we have done quite a few examples to show how principle of conservation of mechanical energy can be used to determine the height or the speed of a certain position, okay, in this situation here.